Hi everyone, welcome back for today's class. Are you ready for today's class? Today we will discuss potential due to an electric dipole. Okay, first we will draw the diagram. So imagine a dipole, electric dipole. You know what is a dipole? System of two equal and opposite charges separated by a small distance. That is known as an electric dipole. So I am drawing an electric dipole. I am drawing an electric dipole. So here a charge minus Q is kept. This is charge minus Q. This is charge plus Q. So this is an electric dipole. Distance between these two charges, we denote by 2a. That is the length of the dipole. I am marking the center of the dipole. O is the center. The negative charge, I am naming it as A. Positive charge B. I am going to find out the electric potential due to this dipole at an arbitrary point. See, I am taking a point here. This point I name as P. I consider a point here. This point I am taking as P. Now, I am joining A to P. This distance is AP. That is the distance of the point P from the charge minus Q. I name it as R1, this distance. And again, I'm joining the distance from B to P. This distance I'm taking as R2. R2. This distance is R2. R2. Charge is at the point B. Charge is at the point B plus Q. So I'm going to find out the potential at P. Obviously, there will be two potentials. At the point P, potential due to minus Q and potential due to plus Q, both are present. So we have to add this. So let V plus Q be the potential at the point due to the charge plus Q. Potential at the point P due to the charge plus Q. Similarly, V minus Q, potential at the point due to the charge minus Q. So at the point P, total potential is the sum of this. Total potential at P is, what is the total potential at P? You have to add it, V minus Q plus V plus Q. Okay. Now you see the diagram. I am joining the point O. O is the midpoint of the dipole. O to the point P I am joining. This distance OP I take as R. Okay. We have to do some assumptions in this question. See, if you extend the line OP this way, see, extend the line OP. Mark this point as N. So you extend the line OP, this point N. Now you drop a perpendicular from A to N. So A to the point N, you drop a perpendicular. This point is N. Okay. This angle will be 90 degree. This angle you mark as theta. Theta. And you know the dipole length is very small. The center of the dipole we consider as the point O. So we know the dipole length is very small. So this distance is A. AO is half the dipole length. Similarly, BO is A. Since dipole length is very small, we can assume that AP nearly equals AN. Since the dipole length is very small, we can write AP nearly equal to NP. Okay. In the same way, if you drop a perpendicular from the point B to R, see this drop a perpendicular from the point B to R. That point you take as M. Same way we can write R2 nearly equal to PM. Or we can write PB nearly equal to PM. Because the dipole length is very small. That is why we are assuming. You know, dipole length is in millimeters or less. Okay. Now, you consider the triangle ANO from the triangle ANO. You can find out the cos theta. What is cos theta? Adjacent of the triangle is ON. Adjacent side of the angle is ON divided by hypotenuse. What is hypotenuse? AO. AO is A only. So ON by A. So we can write ON is A cos theta. Okay. In the same way, when you consider the triangle BMO from triangle BMO, you consider the triangle BMO. Same way we can take cos theta. Cos theta is OM by A. So we can write OM as A cos theta. Okay. So this is the explanation of diagram till now. Now what we are going to do is, I'm calculating the distance AP. I told you AP is nearly equal to NP. Okay. So what is NP? NP is OP plus ON. We can write NP. You see the distance NP, N to P, that distance. That can be written as OP plus ON. So I am writing NP equals, we can write OP plus ON. And OP is R. We labeled OP as R. Plus ON we found out from the triangle. See what is ON? See this here it is ON. ON is A cos theta. So A cos theta. So this NP is nearly equal to AP that you take as R1. So we can write R1 equals R plus A cos theta. So we found out R1 in terms of R and A, dipole length A. R1 equals R plus A cos theta. Similarly, you can find out R2. See from the figure, you can write PB equals, what is PB? PB equals R2. And we can write PB equals, see PB is OP minus OM. So PB is R2. What is OP? R minus OM. OM we found out here. A cos theta. A cos theta. Okay. So R2 equals R minus A cos theta. Okay, children. I think it is clear till here. Okay. Now, you know the equation for potential. Total potential was what? Total potential was, we wrote the equation. Total potential is V plus Q plus V minus Q. Add the two potentials. Okay. And V plus Q, you know the equation. K Q divided by, what is the distance from plus Q to P? R2 plus V minus Q, potential due to the charge minus Q, K minus Q divided by R1. Distance from that charge is R1. But you found out the value of R1 and R2. So we can take common things. What are the common terms? K is common there. Q is common. Remaining is 1 by R2 minus 1 by R1. Clear? Now V is equal to K into Q into bracket you put, what is 1 by R2? R2 we obtained as R minus cos theta. 1 by R minus cos theta. Minus, what is 1 by R1? 1 by R1 is R plus A cos theta. Okay. Now we have to simplify. We take the LCM. V equals KQ. Take the LCM. LCM is R plus A cos theta into R minus A cos theta. R plus A cos theta. Upon numerator will be what? R plus A cos theta minus R minus A cos theta. Now from the numerator you can cancel some terms. Opening the bracket from the numerator, what we are getting? KQ into, see, here plus R minus R cancel. Numerator A cos theta minus A cos theta. What you are getting? 2A cos theta divided by denominator. What is the form? A plus B into A minus B. So you can write R square minus A square cos square theta. Okay. Then this can be written as K into Q into 2A. I am writing together. Cos theta divided by R square minus A square. R square minus A square cos square theta. But you know, Q into 2A is dipole moment, P. So Q into 2A we can write as dipole moment. So what is the equation for potential? V equals K P divided by R square minus A square cos square theta into cos theta. Now, you know, in the denominator, A is very small. A is dipole length. It is of the order of 10 raised to minus 3 and even less, I told you. So when you take the square of 10 raised to minus 3, suppose 10 raised to minus 6, it is 0.00001, right? So that is neglected compared to R. Since A square is very small compared to R square, we neglect A square cos square theta. Therefore, what you are getting? K P by R cos theta. So this is the equation for the electric potential at a point, at an arbitrary point due to a dipole. So what is V? K, you know, 1 by 4 pi epsilon 0 P cos theta by R. So this is the equation for the electric potential at an arbitrary point for an electric dipole. Okay, V is equal to 1 by 4 pi epsilon 0 P cos theta by R. What is P? P dipole moment. R is the distance from the center of the dipole to the point. This derivation is very important. Now we can discuss some special cases. See, we know the equation V is equal to, for a dipole, 1 by 4 pi epsilon 0 P cos theta by R. So this is R square, not R. See, in the denominator, R square is there. We neglected A square cos square theta only. So it is P cos theta by R square. So this is the equation for the electric potential. Now, as first case, if we consider the point on the axis of the dipole, see, this was minus Q plus Q dipole. Okay, this distance was 2A. If we consider the point here along the axis, so initially we considered the point here only, right? In the derivation, we consider this point, right? This angle was theta. If you take the point, consider that point P on the axis, what is the value of this theta? Theta will be 0. So what will be V? 1 by 4 pi epsilon 0 P cos 0 by R square. So V equals 1 by 4 pi epsilon 0 P by R square. This is the equation for the electric potential at the axial line of a dipole. Okay. Now, as a second case, what will be the potential on the equatorial line of the dipole? Electric potential at a point on the equatorial line of the dipole. So, case 2. At a point on the equatorial line. Okay. So at a point on the equatorial line of the dipole. First case was what? At a point on the axial line. This was the first case at a point on the axial line. So what is the potential at a point on the axial line of an electric dipole? 1 by 4 pi epsilon 0 P by R square. Now, what about the equatorial point? See, I will draw the diagram. This is minus Q charge plus Q charge. This is a dipole, 2A. You know, equatorial line is the perpendicular bisector. So this is the equatorial line. Okay. Initially, in the derivation where we consider the point, we consider the point P here, and this angle was theta. If you consider this point on the equatorial line here, what will be the theta then? If you take the point P on the equatorial line, we are considering the point P on the equatorial line here. What will be this angle? This angle will be 90 degree. So theta is 90 degree. So what will be the potential? V equatorial. 1 by 4 pi epsilon 0 P cos theta by R square. But theta is 90 degree. P cos 90 by R square. So you know what is cos 90? 0. So V equatorial is 0. So remember, electric potential at a point on the equatorial line is 0. Okay. What is the electric potential at a point on the axial line? V axial equals 1 by 4 pi epsilon 0 P by R square. What is the value of equipotential potential on the equatorial point of a dipole? It is 0 because this theta become 90 degree, right? So at all point on the equatorial line, the value of electric potential is 0. Here, one thing you have to remember, if you want to move a charge along the equatorial line, what should be the work done? No work is to be done because potential is 0, no potential difference at any point on the equatorial line. Okay, this derivation is an important derivation for the board exam. Okay. Now, next topic is equipotential surfaces. Equipotential surfaces. You know the name itself, equipotential, equal potential. So what is equipotential surface? It is a surface of constant potential. So what is equipotential surface? It is a surface of constant potential. On this surface, potential is same everywhere. So equipotential surface is a surface of constant potential. So on an equipotential surface, there is no potential difference. Potential is same everywhere. Now, what is an example? You consider a point charge. I'm drawing I am giving an example how to draw equipotential surface. You consider a point charge. See, this is a point charge. You consider points at equal distance in all directions. Okay? At equal distance in all directions. So if you join all these points, you are getting a spherical surface. Okay? Spherical surface. If you join all these points, we get a spherical surface. It is a sphere of radius r. And you know potential equation V equals KQ by R, potential at a point. So R is same, charge is at the center. So these points will be all are at the same potential. So when we consider the spherical surface surrounding the charge, point charge Q, potential is same everywhere on this spherical surface. So this is an equipotential surface. So an equipotential surface, an example for a point charge, what is the shape of an equipotential surface? Sphere. For a point charge, equipotential surface is a sphere. And your field lines, the field lines, electric field lines will be perpendicular to the equipotential surface. Electric field lines will be perpendicular to the equipotential surface. So what do you mean by an equipotential surface? It is a surface of equal potential. When you consider a point charge surrounding it, there are many equipotential surfaces. For a point charge, equipotential surface is a spherical surface. See, I can draw many spherical surfaces around a point charge. So this is another equipotential surface. So for a point charge, equipotential surfaces are spherical surfaces, concentric spheres. Another spherical surface. Okay, so for point charge, equipotential surfaces are concentric spheres. Okay, so what is an equipotential surface? Children, what is an equipotential surface? It is a surface of constant potential. What is the shape of equipotential surface for a point charge? Concentric spheres. Now, I am drawing equipotential surface for a uniform electric field. You know, how will you draw a uniform electric field? How will you represent? Uniform electric field is represented by parallel equidistant lines. This is a uniform electric field. So if you take a plane like this, at all these points, at all points on this plane will be equal potential. See, at this point, this point, everywhere potential same. So this plane is, this rectangular plane is an equipotential surface. So equipotential surface for a uniform electric field is planes. So I have drawn two equipotential surface here. Okay, for a constant electric field, equipotential surfaces will be equidistant surfaces. These planes are equidistant. Okay, this is the equipotential surface for a constant electric field. Equipotential surface, what is the shape? These are plane surfaces. They have equal distance, right? Now we can draw equipotential surface due to a dipole. How will you draw the equipotential surface for a dipole? Dipole, you know, system of two a system of two equal and opposite charges. So this is a negative charge and this is a positive charge. Equipotential surface will be, you know, along the axial line, you know, for a dipole electric field decreases. You know, Kp by E is equal to Kp, E equals K2p by R cube. So along the line potential axis, potential decrease. So shape will be like this. There won't be exact spheres around each charge. It is distorted like this. This is point for negative charge. Similarly, around positive charge, so these are the equipotential surface for a dipole. Okay. And along the center of the dipole, potential at all points will be same. You learned the last derivation. At equatorial potential, equatorial line potential is 0. Okay. So this vertical plane I have drawn at the center. This plane is also what? Equipotential surface. So this is the equipotential surface for a dipole. Okay. Now we can draw the equipotential surface for a system of two positive charges. Equipotential surface for a system of two positive charges. Okay. Then you consider one positive charge, another positive charge. So you know it will be like this for each charge. It will be like this. It will be like this. This is the shape of the equipotential surface for a system of two positive charges. So what are equipotential surface? What we learned? It is a surface of equal potential. right? Potential will be same at all points of the surface. So we have drawn equipotential surface for a point charge. It is spherical in shape, spherical surfaces. So for a point charge, equipotential surfaces are concentric spherical surfaces. For a uniform electric field, what is the shape of the equipotential surface? Parallel planes. And we have drawn equipotential surface for dipole and a system of positive charges. See these diagrams, you look in the textbook and draw exactly. My diagram is not so perfect. Okay. Now we can learn the properties of equipotential surface. See, equipotential surfaces properties. Two equipotential surfaces never intersect. What is the reason? If two surfaces intersect, then there will be two directions for electric field at that point, which is not possible. If they intersect, there are two directions for electric field at that point, which is not possible. First property. Second property, electric field is always perpendicular to the equipotential surface. Why it is perpendicular to the equipotential surface? If it is not perpendicular, what will happen? There will be a component of electric field which make the charges move over the surface. That is not possible. So properties of equipotential surface. Properties of equipotential surfaces. What are the properties of equipotential surfaces? First property, they never intersect. They never intersect. Why they never intersect? If they intersect at a point, there will be two directions for the electric field at that point, which is not possible. At one point, there can be only one direction for electric field. Second, electric field is always perpendicular to the equipotential surface. Perpendicular to the equipotential surfaces. Okay. Why it is so? Suppose this is an equipotential surface. Electric field has to be like this. Suppose electric field is in this direction, making some angle as shown by the dotted line. If it is like this electric field can be resolved into two components. E sin theta components will be along the surface. That will make the charges move. That means there exists a potential difference across the surface. It is not possible. You know, equipotential surface means all points are at the same potential. So there cannot be a potential difference. That is why the reason electric field is always perpendicular to the equipotential surface. Now third, you know, at all points on an equipotential surface, potential is same. So work done to move any amount of charge on an equipotential surface will be zero. Work done to move any amount of charge on an equipotential surface is zero. Why? You know the equation for work done. Work done is charge into potential difference, say VA minus VB. But VA equals VB, right? For an equipotential surface, same potential. So this work done will be 0. So what is the amount of work done to move 2000 coulomb of charge on an equipotential surface? 0. Why the work done is 0? Because equation for work done is Q into potential difference. Since same potential at all points on an equipotential surface, the work done will be 0. These are the properties. One more property we can say, when the field is stronger, equipotential surface will be crowded together or closer together. You know this equation, E equals minus dV by dr. We learned electric field is the negative gradient of potential. For constant potential, E proportional to 1 by dr. That means when the field is strong, the spacing between the equipotential surface will be the same, will be decreasing. See, you are considering an electric field, strong electric field. Suppose there is an electric field that magnitude increases along x-axis. Okay, field magnitude increases along x-axis. As move along x-axis, field is increasing. So what will be the equipotential surfaces? Then you can see the equipotential surfaces, spacing between them decreases like this. Planes of same area, but what will happen to the distance between them? Distance between them will decrease. See, these are the equipotential surfaces in an electric field whose magnitude increases along x direction. So when magnitude of electric field increases, the spacing between the equipotential surfaces goes on decreasing. This is an important property. Okay. So what we learned today, we learned the derivation for a potential due to a dipole. And we have seen that along the equatorial line of an electric dipole, potential is 0. Then equipotential surfaces. What are equipotential surfaces? They are surfaces of constant potential. It is a surface where potential is same on every point on it. And we learned shape, equipotential surface shape for a point charge. For a point charge, equipotential surfaces are spherical surfaces, concentric spheres. For a uniform electric field, equipotential surfaces are plane surfaces. Okay. And for a dipole, we have drawn this shape. This is very important. Maybe for a short question, they may ask, draw the equipotential surface for a dipole. Now, next we learned properties of equipotential surfaces. What are the properties of equipotential surfaces? First property, two equipotential surfaces never intersect. Why they never intersect? If they intersect at one point, there will be two directions for electric field at that point, which is not possible. Second, electric field is always perpendicular to the equipotential surface. Why it is so? If electric field is not perpendicular, if it is making an angle like this, then there is a component of electric field along the field direction that make the electrons move over the surface. It is not possible. Electrons can move whenever there is a potential difference. So there is no potential difference. Okay. Work done to move any amount of charge on an equipotential is surface is 0. These are the properties of equipotential surfaces. Okay, children. Today I am stopping the class. Thank you for watching the video. Children, share, subscribe. Okay, write your comments. Goodbye for today's class.